In this part of the course, we're going to talk about interpolation, and specifically in this clip, we'll talk about polynomial interpolation. But first of all, let's discuss the question of what is interpolation all about. Well, if you sort of roll back to the time when we didn't have computers and calculators and whatnot, and you wanted to find, let's say, the sign of some function, so you wanted sine of x, you basically had a book of tables where you looked up the values. So the book would tell you, for example, that the sine of 0.123 is equal to such and such a value, and the sine of 0.124 is equal in such and such a value, and that was the only way that you could actually get the values of the sine function, apart from somehow trying to calculate this yourself. So the question that was asked is, what if you want to find out the sine of, let's say, 0.1235? Now, this isn't in the table, so instead what you have to do is you have to somehow read between the lines, so to speak, and figure out what the sign of the value is based on some values that you already know. And this is ultimately what interpolation is all about. It's about reading between the lines. So the general idea of interpolation is that if you are looking if you've got a function of x, like for example sine of x or something, then given a number of points, you might be looking for some other function which also coincides with those points. So it might be, for example, a polynomial, some polynomial of x, which is equal to the function of x at specific points. So essentially you might have a couple of points, let's say x1, x2, x3 and so on up to some xn value, and you already have those points. You know what the function, let's say the sine of x is at those points, and you would be looking for a polynomial which also coincides with these points. So let's take a look at an example. So for example, let's suppose that my f of x is going to be equal to e to the power of minus 1 over x. 1 over x, like so. So essentially what I'm going to have is I'll just have a table of just a few values. Typically you would consider just a couple of values, maybe like 5 or 6. We'll consider 3 values here. So let's suppose I have the values at 1.1, 1.2, and 1.3. So my function f of x, or maybe I'm reading a table somewhere, or maybe I've calculated it myself, I have the values 0.4029, 0.4346, and 0.4634. Okay, so these are the values I have, and let's suppose I am looking for some value that's in between. Maybe it's 1.15 or something else. I want to get a polynomial which actually goes through these 3 points. So how do I get it? Well, if I'm looking for a polynomial p of x, which is defined, let's say we have a second order polynomial, so that would be ax squared plus bx plus c. What I can do is I can take these values of x and I can plug them into the polynomial, and on the right hand side I would be expecting the same values of y as the original function. So essentially what we get out of all of this is we get a system of equations. So we plug in the values and we get a system of equations. So 1.1 squared, for example, is 1.21a plus 1.1b plus c being equal to the right hand side, so that's 0.4029, and we get similarly the other 2 equations. So we get 1.44a plus 1.2b plus c equal 0.4346, and 1.69a plus 1.3b plus c being equal to 0.4634. And so you solve the system of equations and you get the values of a, b, and c. So you get a equals to minus 0.145. Now, before I continue, I have to say that at this moment, we cannot really assume that there is even a solution to all of this, because the coefficient matrix may as well be singular and we might not get solutions. But in this particular case, because I'm doing this demo, we are lucky. We have a solution, and that solution is as follows. So I've got the value of A, the value of B is equal to 0.6505, and the value of C is equal to minus 0.1372, and we can plug in these values A, B, and C into the polynomial, and what we get is the following. So we get the polynomial of x being equal to minus 0.145x squared plus 0.6505x, and then minus, it should be a minus, so minus 0.1372. So we essentially have a polynomial which at points 1.1, 1.2, and 1.3 gives us the same result. So if you want the polynomial to be evaluated at a point 1.15, for example, you would simply plug it into the polynomial function here, and you would get an approximate estimate based on this polynomial interpolation. So I just want to show what the end result looks like in MATLAB. All I'm doing here is a plot of the two functions, the e to the minus 1 over x and the polynomial, and I'm plotting them from 0 to 2. So let's run this, let's see what we get. So here we are, let me stretch it a little bit, and as you can see, we're having the blue line is the actual function. So you can see that at x being equal to 0, for example, it's really far away from what the function actually is. But we're only interested in the 3 points which are shown with the x's here, and it looks as though the points more or less coincide, and as a result we can argue that the polynomial evaluated at some in-between point, like here for example, would be approximately equal to the actual function. And that's what interpolation is all about. Now, one thing I wanted to mention is the example that's being shown here is only for illustration. In the real world, you will not be constructing the interpolation polynomials in such a direct manner as to solve a system of equations. That's not something that is typically done. It's especially a bad idea if you have a polynomial of a high degree.